This short video is to go along with the PowerPoint on molarity, molality, and mole fraction. So if you were watching that PowerPoint and you weren't exactly sure what to do, hopefully this will help answer some questions for you. So we're going to first look at our equations, right? Molarity, we have moles of solute over liters of solution. It's important that you keep the units of moles and liters when you are doing problems such as these. So to clarify, right, what is a solute? A solute is a substance that is being dissolved. So let's say you are making Kool-Aid. You are going to take your Kool-Aid mix, which is going to be your solute, and you're going to dump that into water, which is your solvent. And when you mix your Kool-Aid, your solute, with your water, your solvent, the end result, you get a solution. And that solution is made up of both your solute and solvent. So in the case of this answer, right, you want the total volume of your solution if that happens to change when you put in your solute. Looking at mole fraction, right, that's simply in moles, so we're okay there. Just make sure that you're doing the total moles of the whole entire substance. Molality, again, moles of solute. Now, instead of liters of a solution, you're doing the kilograms and you're doing the solvent only. You're not doing the whole entire solution for that problem. When you are writing out your answers and attaching units to it, the units for molarity is going to be a capital M. The units for molality is a lowercase m. And for mole fraction, you could put MF, but essentially it's going to be a decimal number that doesn't really need units. So let's work on number 1. Okay, what is the molarity? So of course we know that our equation is going to be molarity equals, right, moles over liters. So what is the molarity of a solution in which 58 grams of NaCl is dissolved in 1 liters of solution? Well, we need moles and liters, and we've got grams. So don't get sucked into using molality because you see the units of grams. What you have to do is you have to take that 58 grams of salt, right, NaCl, and you're going to have to figure out how many moles that is. If you think back to your previous units, you know how to convert grams to moles. Right? We want the units of grams to cancel out, so we're going to put the grams of NaCl on the bottom, and we want to get to the moles of NaCl. Well, in order to make that conversion, if you remember from the past, you are going to figure out the molar mass of NaCl, right? In 1 mole, the molar mass of it is 58.5 grams. Remember, you're taking from the periodic table, you're taking the atomic mass, right, of Na to 1 decimal place. You're adding it to the atomic mass of Cl to 1 decimal place, and then solving for the moles. So our units of grams is going to cancel out. When you take 58 and divide it by 58.5, you get 0.9915 moles. I'm carrying that out to more decimals than needed for significant figures, just because I'm going to make another calculation. So on to finally using this equation. We now know the number of moles, right, are 0.9915. The liters is given to us in the problem. It tells us we have 1 liter of solution, and so we're solving for that molarity. And that molarity comes out to be two significant figures, right? And 58 has two significant figures. So if you're in honors chemistry, of course, you want all your answers in significant figures. If you're in the general ed chemistry, then it doesn't really matter. So our answer will be 0.99, and we're adding the capital M at the end for molarity. Moving on to number 2. What is the molality of a solution in which 3 moles of NaCl is dissolved in 1.5 kilograms of water? So it's in the water, so this is our solute. Our salt is the dissolving agent, or the thing that's dissolving, so that is our solvent. And remember that molality, right, lowercase m, is equal to our moles of solute over our kilograms of solvent. Well, we're already given those values. We know that we have 3.0 moles of NaCl, which is two significant figures. We know that we have 1.5 kilograms of water, and be careful, it's in the proper units. A lot of times you'll see it given, the mass will be given to you in grams. So solving for that molality to significant figures, we would want 2 sig figs. We have not just 2, but 2.0, so we have the correct number of significant figures. And again, the unit of measurement is just that lowercase m. So there is your molality example. Moving on to number 3. What is the mole fraction of O2 in a mixture that contains 4.5 grams of O2 and 9.9 grams of H2? Well, mole fraction has to be in moles. We're dealing with mass, right? We have 4.5 grams and 9.9 grams, so we need to convert those into moles using the same idea that we were using in number 1. So 4.5 grams of O2. We know that the molar mass of oxygen, right, is not just 16, but it's 32 because it's O2, right? There's 2 of them. So we have 32 grams for every 1 mole of oxygen, and that gives us 0.1406 moles of O2. Moving on to our hydrogen, we start off with 9.9 grams of hydrogen. Again, that's H2, not just H, so the molar mass of H2 is 2, not just 1. Right, so for every mole of H2 you get 2 grams. That converts to 4.95 moles of H2. We are now ready for our mole fraction, right? Mole fraction is equal to the moles of our one substance, right? Oops, that should just be an O. Our O2 over not just the moles of H2, but over the total moles of your whole entire substance. So solving for that mole fraction, right, we know that we have 0.1406 moles of O2. We have the total, right, which is 0.1406 moles of O2 and 4.95 moles of H2. So and these are all in moles. So because everything is in moles, that means that essentially this answer has no units. So the mole fraction is 0.028. Right? Again, no units. This value here is in 2 sig figs. This value here is in 2 sig figs. So my answer has 2 significant figures. The last one, what is the mole fraction of H2? Well, using that same formula, right, we want the mole fraction. In this case, now we want the mole fraction of hydrogen, and again, it's going to be divided by the total amount of moles. So the moles, the total amount of moles for just hydrogen was our 4.95. The total moles is the same as before, 0.1406 plus 4.95. And of course, our units cancel out again, leaving us with 0.97 is our mole fraction. And again, two significant figures. What these values mean is basically it's kind of like a percent. If you were to think about multiplying this number by 100, you would get 0.28%, right? Or sorry, can't do math in my head, 2.8%. And if you were to multiply this number by 100, you would get 97%. So our solution in this case is 97% hydrogen and 2.8%, and again we're rounding so it's kind of closer to 3, right, is 3% oxygen. Hopefully this helps you out, and let me know if you have any questions.